Could Kilauea really be shifting the ground by nearly 3 centimeters every time it erupts? That is the claim making the rounds online, but the real story is more useful and more interesting than the headline version. The colorful satellite maps are not showing a fixed 2.8 centimeters per eruption. They are showing something subtler, the scale of the map itself. One full color cycle on those interferograms represents about 2.8 centimeters, or about 1.1 inches, of motion along the satellite's line of sight. That is not a limit. It is not a rule. It is not the size of each eruption cycle. It is a measuring step, the spacing of the rainbow bands scientists use to read the volcano's movement. So the real question is not whether Kilauea moves 2.8 centimeters every time it erupts. The real question is this: how much motion is hidden in the stacks of fringes, and what does that motion tell us about magma underground? That is where the geology gets interesting. Kilauea is not just a hole in the ground that occasionally throws out lava. It is a living plumbing system. Deep below the summit and rift zones, magma is stored, moved, squeezed, released, and replenished. That movement changes the shape of the ground above it. Sometimes the summit swells, sometimes it sinks. Sometimes a rift zone opens a little, or a dike forces its way sideways through the crust. These changes are too broad to see by eye, but satellites can catch them in exquisite detail. The science behind that view is interferometric synthetic aperture radar. It sounds technical because it is, but the basic idea is simple enough. A radar satellite passes over the volcano, bounces microwave signals off the surface, and records the distance between the satellite and the ground. Then it comes back later and repeats the process. If the ground has moved, even by a few centimeters, the returning radar waves no longer match perfectly. The difference shows up as a colored fringe pattern on the map. Those fringes are the key. They are not decorative. They are not random bands. They are the visual record of phase change in the radar signal. In plain terms, they are a ruler built from interference. Each full color cycle corresponds to one complete radar phase wrap, and for Sentinel satellites data that commonly works out to about 2.8 centimeters, or about 1.1 inches of motion along the line of sight. That means one fringe is one increment. Two fringes are about 5.6 centimeters, or about 2.2 inches. 5 fringes are about 14 centimeters, or about 5.5 inches. 10 fringes are about 28 centimeters, or about 11 inches. The map is not saying the volcano moved only 2.8 centimeters. It is saying each band marks another 2.8 centimeters of change. If the ground moved farther, the colors simply keep cycling. That distinction matters because it changes the meaning of the image. A person seeing the first band around a summit might think the system shifted a small amount and stopped there. In reality, the ground could have moved many times that amount. The fringe count is the clue. At Kilauea, scientists often see broad bullseye patterns around the summit caldera, especially when magma is refilling a shallow reservoir beneath Halamaumau. That pattern usually means inflation. The ground rises because magma is entering or pressurizing the storage zone. Later, when magma is withdrawn for eruption, the same area can show the opposite pattern. The summit deflates. The caldera floor sinks. The color bands reverse in the sense of motion, even if the map itself still uses the same scale. That is the volcano breathing in and out. The temptation in public discussion is to reduce all this to a single number, but volcano deformation does not work that way. The amount of motion depends on how much magma moves, where it moves, how quickly it moves, and how the crust responds. A shallow storage zone can inflate more dramatically than a deeper one because the surface is closer to the pressure change. A narrow intrusion along a rift may make a very different pattern from a broad pressurization under the summit. The same eruption style can produce a different deformation footprint depending on whether the magma stays mostly in the summit reservoir, feeds a fissure, or drains into a rift dike. That is why 2.8 centimeters per cycle is not a cycle total. It is only the unit of the map. At Kilauea, that unit is especially useful because the volcano is so active and so instrumented. The summit has a shallow magma chamber beneath Halamaumau, and the volcano also has east and southwest rift systems that act like long, broken pathways for magma. When magma rises into the summit reservoir, it pushes outward on the surrounding rock. The roof of the chamber bows upward. The surface may rise by several centimeters or by far more, depending on the amount of recharge. When an eruption begins, magma exits the reservoir and pressure drops. The roof can sag, the summit can subside. If the eruption taps a rift, the deformation may shift away from the summit and become more linear or asymmetric, reflecting the geometry of the dike or intrusion. The ground is not moving in one simple way. It is responding to a changing network of pressure, fractures, and magma flow. This is why INSAR is so powerful. Traditional ground instruments, such as tiltmeters and GPS stations, tell scientists what happens at a point. INSAR gives them a wide view. It shows how the entire summit or rift segment moves, not just one benchmark or one sensor. That broader view is important because a volcano does not deform like a rigid block. It bends, it tilts, it stretches, it compresses, it sinks in one place while rising in another. INSAR can reveal all of that at once, as long as the surface is visible to the radar and the vegetation or eruption plume does not obscure the signal too badly. For Kilauea, that makes satellite deformation maps especially valuable during repeated eruption cycles, because the volcano can shift from inflation to deflation and back again over days or weeks. The term cycle also deserves care. In casual language, people may think of an eruption cycle as one event, a fountain, a lava outpouring, then silence. Geophysically, the cycle is more complicated. There is a recharge phase, when magma accumulates and pressure builds. There may be a threshold where the system fractures or reopens. There is a release phase, when magma drains and the ground responds. Then there is the recovery phase, when the reservoir refills again. In the current summit eruption sequence, the episodes can be short, sometimes lasting less than half a day, and they can be separated by pauses of days to weeks. During the pause, the summit may inflate. Right before eruption, the deformation can become more pronounced. After lava fountains or vent activity, the summit may deflate. The total change across the whole span can be many fringes, which means many increments of 2.8 centimeters. The important point is that there is no fixed one fringe per eruption law. The ground motion depends on the volume and timing of magma transfer. Some of the most revealing interferograms from Kilauea show nearly circular banding around the summit. Those are the classic bullseye patterns. They often point to a centered pressure source beneath the caldera. When the circles are spaced in a way that indicates uplift, the interpretation is usually that magma is charging the reservoir. When the circles show deflation, the reservoir is losing magma. That loss can happen because magma is erupting at the surface, but it can also happen because magma is moving into cracks or dikes below ground. The satellite does not directly see the magma. It sees the ground's reaction to the magma. That distinction is crucial. The bands are not lava. They are the crust bending under the movement of lava and gas-rich melt below. The summit chamber beneath Kilauea is especially important because it sits relatively shallow. United States Geological Survey discussions of these episodes often describe the reservoir as being on the order of about 1.5 kilometers deep, or about 0.9 miles deep, beneath Halama'umau. A shallow chamber means changes in pressure can translate quickly to the surface. When magma collects there, the roof can rise. When magma leaves, the roof can drop. The surface record is therefore a kind of pressure gauge. It does not tell scientists everything, but it tells them a lot. It helps them infer whether the reservoir is being charged, whether it is draining, and how the plumbing is evolving over time. The deeper structure matters too. Kilauea's rift zones are not static cracks. They are long, weak pathways in the volcanic edifice that can open under stress. A magma intrusion into the east rift zone can create a different fringe pattern than one centered on the summit. Instead of a neat bullseye, scientists may see elongated bands or a butterfly-style arrangement that reflects extension along a line. That lineation suggests the deformation source is not just a point under the summit, but a source with a preferred direction, often tied to a dike. A dike is a sheet-like body of magma that forces its way through fracture networks. When a dike opens, the surrounding rock can separate slightly, producing deformation patterns that mirror the geometry of the intrusion. In other words, The pattern itself is a clue to the plumbing. Eruption cycles are not identical pulses. A summit fountain that mostly empties the shallow reservoir may cause strong deflation. A quieter episode that only taps a portion of the stored magma may cause less. An intrusion that never reaches the surface may still create major deformation because magma is moving underground without erupting. Even the same style of eruption can produce different amounts of ground motion depending on how much magma is transferred and how quickly the system responds. The deformation is the result of balance between supply and release. That balance changes from episode to episode. It helps to think in terms of volume and pressure, not just distance. A small amount of magma entering a shallow chamber can cause a noticeable uplift if the chamber is small or if the crust above it is flexible. A larger amount of magma moving deeper in the system may create less surface motion if the source is deeper or the deformation is spread over a wider area. Pressure can rise without a large visible displacement if the system is stiff. A smaller pressure change can create larger motion if the source is shallow and the rock is more compliant. That is why scientists rarely treat one fringe count as a direct volume measurement. They combine the satellite data with ground sensors, eruption timing, seismicity, gas output, and physical models of the magmatic system. The physical basis of the fringes is phase wrapping. Radar waves have a wavelength, and when the phase shift between two satellite passes reaches one full cycle, the color resets. That reset creates the familiar rainbow banding. It is easy to misread because the eye sees color changes before it sees measurement, but the fringes are just contour lines in disguise. They show equal increments of line-of-sight displacement. If the ground moved toward the satellite, the phase changes in one direction. If it moved away, the phase changes in the other direction. The sign of the motion matters, but so does geometry. Because the satellite looks from the side rather than straight down, the map records only the component of motion toward or away from that viewing angle. A vertical uplift of the ground does not appear one for one in the radar measurement. A sideward shift does not either. The observed displacement is a projection of the actual three-dimensional motion onto the satellite's line of sight. That projection is one reason careful interpretation is needed. Suppose part of Kilauea's summit rises straight up by 12.7 centimeters or 5 inches. The satellite may record a smaller line of sight change because the radar beam is not vertical. The same is true for horizontal motion. If the surface moves sideways, some of that shift may or may not be visible to the radar, depending on direction. So when people say the fringes show uplift or subsidence, what they really mean is that the ground moved closer to or farther from the satellite in the radar geometry. Scientists understand that shorthand, but the distinction matters when translating the image into physical ground movement. The eruption episodes at Kilauea since late 2024 have made this especially clear. The summit does not simply erupt and then return to a fixed state. It inflates, then deflates, then reinflates. The cycles reflect a working magma reservoir that is being replenished from below and drained from above. The timescale can be days to weeks. The motion can be broad and smooth or concentrated and sharp. During one episode, a map may show a tight cluster of rings around the caldera floor. During another, the deformation may spread farther across the summit or into the rift. The pattern tells scientists how the pressure field is changing. It also hints at where the magma is going, even when the lava itself is only visible for hours. The broad deflation around the summit during some episodes is especially revealing. Deflation means the reservoir is losing mass or pressure. That can happen because magma is erupting through a vent, but it can also happen because the reservoir is feeding an intrusion that does not erupt at the surface. In both cases, the roof of the chamber can sag. The surrounding ground can settle. The fringe map then records a ring pattern that marks this downward motion over the observation window. Because the observation window may span several days, the total motion can be much larger than one fringe. Multiple cycles of 2.8 centimeters accumulate, and the map becomes a stacked record of that change. The same logic applies to inflation. When a pause opens between eruption episodes, magma may continue rising from deeper levels into the shallow reservoir. Gas exsolution can increase pressure as the magma ascends and volatile components separate from the melt. The chamber grows more pressurized. The ground above it bulges upward. INSAR may then show concentric bands that are the mirror image of the earlier deflation pattern. Again, the important point is not that the volcano moved a fixed amount, but that the volcano moved in a direction consistent with recharge. Inflation is the crust responding to an increase in internal pressure. Deflation is the crust responding to a decrease. Scientists use these patterns not only to measure motion, but to infer mechanism. If the deformation is centered and circular, a shallow pressure source is likely. If it is elongated, a rift intrusion or dike may be involved. If it is asymmetric, the magma body may be tilted, segmented, or interacting with pre-existing structures. If the deformation changes quickly, the system may be responding to abrupt magma transfer. If it changes slowly, the magma may be moving in a more gradual way. In that sense, the fringe map is like an X-ray of the volcano's stress response. It does not show the magma directly, but it shows the effect of that magma on the surface. This is also why one should be cautious about saying that the volcano moves every cycle by some single number. Nature does not favor tidy repeating values in a system as complex as Kilauea. The rate and amount of ground motion can vary from one episode to the next because the source volume varies, the conduit conditions vary, and the surrounding rock varies. Sometimes the reservoir may be nearly full and a small withdrawal produces a noticeable drop. Sometimes the system may absorb pressure without much surface motion. Sometimes intrusions into the rift can redistribute stress in ways that make the summit move differently from the flanks. The same volcano can display different behavior over the course of a single eruption sequence. Yet the public fascination with the 2.8 centimeters figure makes sense. It is a clean number. It is easy to repeat. It sounds like a dramatic revelation. But the investigation of the image shows a better story. The satellite is giving us a scale, not a verdict. The value is the spacing of the ruler, not the size of the event. Once that is understood, the rainbow maps become more meaningful, not less. They stop being a curious color puzzle and become a real record of magma transport. Each fringe is one increment of motion. Each cluster of fringes is a timeline of inflation or deflation. Each pattern is a clue to where the magma is stored, how it moves, and how the volcano's plumbing responds. And that is why the question should never be, did Kilauea move only 2.8 centimeters? It should be, how many fringes are there? What direction do they point, and what part of the volcanic system is changing? A few fringes can mean a modest shift. Many fringes can mean a major one. A bullseye can point to pressurization beneath the summit. A lineated pattern can point to intrusion along a rift. A reversal from inflation to deflation can mark the start of a lava discharge. The image is a coded message from the volcano, and the code is physical, not symbolic. Kilauea is a reminder that deformation is often the first visible sign of volcanic change. Before lava reaches the surface, before the fountain opens, before the caldera floor drops, the rock above the magma reacts. It bends, it tilts, it stretches. The satellite sees that response as colored bands. The bands do not prove a single eruption size. They show a process, magma loading the system, pressure building, the surface rising, magma draining, the surface falling, and the cycle repeating as the plumbing resets. That is the real story behind the 2.8 centimeters line. It is not a sensational number. It is the smallest useful unit in a much larger geological conversation. Once you read the fringes this way, the volcano becomes less mysterious and more legible. The summit inflation before an episode is not random. It is the chamber pressurizing. The deflation during an episode is not just collapse. It is magma leaving the reservoir. The east rift patterns are not decorative arcs. They are the surface imprint of intrusion and extension. The repeated cycles are not identical copies. They are snapshots of a system that is always adjusting. Kilauea is showing, in color bands and centimeter steps, the mechanics of a basaltic volcano in motion. The science is not about one number. It is about a process that can be watched, measured, and understood, one fringe at a time.